आगे नॉर्मली ट्रांसफॉर्म बना दो। इससे पहले क्लास की नहीं है 11 बजे? In the previous lecture, we have discussed about the SOR method, spectral radius, and convergence of the iterative method. Also, we discussed about the spectral radius. If the spectral radius of the iterative matrix is less than 1, then the convergence is sure. Otherwise, it is not so. If the convergence is not less than 1, so any of the iterative scheme will not converge. Okay. So now we are going to do some proofs based on the convergence. Okay. Any convergence scheme can be written as, so any iterative scheme, you can write an iterative scheme for the system of linear equation that is x k plus 1 equal to t x k plus b, where k is equal to 0, 1, 2 and so on. Okay, so this T is what? This is called iteration matrix. With the vector. So there is a lemma. If the spectral radius rho of t is less than 1, then I minus t inverse exists and I minus t inverse is equivalent to I plus t square and so on equal to summation tk equal to 0 to infinity. So there is a lemma. If the spectral radius rho of t is less than 1, then I minus t inverse exists. I is what? That is the identity matrix and T is what? That is the iteration matrix. So this T vary according to the particular method. Suppose we are talking about Jacobi method, then T is what? That is D inverse L plus U. If it is a Gauss-Seidel method, then T is what? That is L plus D inverse U. Okay. So let's do the proof of this lemma. Let lambda is the eigenvalue of the matrix T. So we can write it as T and U is the corresponding eigenvector. Then T of U equal to lambda U. Okay. T of U equal to lambda U is the eigenvalue vector. Lambda is the eigenvalue. Then let us apply T on both sides. So what we are getting? T of lambda U. That can be written as T square U equal to lambda. We can write it as T of U lambda. The value of TU is what? The value of TU is lambda U. So it can be written as lambda U square. Okay. Now we'll apply T to T square U. Then we are getting T of T lambda square U. Lambda Q. And continue this process. We are getting T of K U equal to lambda raised to power K U. Since it is given rho of T is less than 1, that means this implies that maximum eigenvalue of the T is less than 1. So all eigenvalue will also be less than 1. So we can write here T of Ku limit K is tending to infinity is equal to lambda Ku. K is tending to infinity, the value is coming out to be 0 because lambda is less than 1. That's why K is tending to infinity, then it is coming out to be 0. So this implies that I plus T square and so on equal to limit K equal to T raised to power K equal to 0 to infinity. It is coming out to be 0 because K is tending to infinity, it is coming out to be 0. So this implies that I minus T, let us multiply here I minus T to I minus I plus T square. Let's multiply by I minus T. So what we are getting, T square and so on, it is coming out to be I minus T into 0. So what is coming out to be? It is coming out to be the matrix as I. So I minus T is equal to, it is coming out to be I. This implies that I minus T is the inverse of I plus T square and so on. So this implies that inverse of I minus T exists, and the expansion of this is what? It is equal to I plus T square and so on. Or we can write it T raised to K equal to 0 to infinity. Okay, how this coming out to be 0? If we will multiply this I minus T, let's do the calculation here. When we multiply I to this matrix, we are getting same T plus T square and so on. now multiply by t, so minus t square and so on. So all positive term get cancelled with this, that's why we are getting here I. This is the identity matrix. Okay, so the lemma is what? If the spectral radius is less than 1, then I minus T inverse exists, and the value of I minus T inverse is what? That is equivalent to this one. Okay, so there is one more theorem. This was the lemma, and this lemma will use to find the convergence of the iterative scheme. So there is one theorem. This is that theorem. A necessary and sufficient condition for the convergence of iterative scheme is that the eigenvalue of iteration matrix T satisfy the inequality rho of t is less than 1. The necessary and sufficient condition for the convergence of the iterative method is the eigenvalue of the iteration matrix T satisfy the inequality, or we can say that the iteration scheme will converge to the, or we can write xk plus 1 equal to T xk plus c for k equal to 0, 1, 2 and so on. Okay, the iteration scheme. The iteration scheme, what is this scheme? Xk plus 1 equal to 2xk. That means any scheme, suppose Gauss-Seidel method, Jacobi or SOR, converges to the unique solution of what is the unique solution? That is x equal to tx plus c. If and only if rho of t is less than 1. That means a spectral radius is less than 1. Okay, so let's do the proof. Okay, just keep in mind, like if the scheme converges to the unique solution, then spectral radius is less than 1, or if the spectral radius is less than 1, then the iterative scheme will converge to the unique solution. So this is, if this condition is there, then the second condition will be sure. If the second condition will satisfy, then the first condition will be sure. So that is the theorem. So let's do the proof of this theorem. We'll assume first part, rho of t is less than 1. Okay, so the spectral radius is less than 1. Let the sequence of the vector xk. Okay, how we are getting this xk? Xk plus 1 equal to txk plus b, x1 equal to tx 0 plus b. Okay, for k equal to 0. K equal to 1, we are getting x2 equal to tx1 plus b. We can write it as t x1. The value of x1 is what? That is from here. The value of x1 from here. that is tx0 plus c. This can be written as t square x0 plus tv. Okay, k equal to 2, x3 equal to t of t square x0 plus x3 equal to t x2 plus c. Now put the value of x2, it is t square x0 plus tp. Okay, so what is coming out to be here? It is coming out to be tq tq, there is one correction, plus p. Okay, plus b. So it is coming out to be here tq x0 plus t square b plus b tv. I'm doing some mistake. Tx square plus p. Now put the value of x0. X0 is what? T square x0 plus tv plus p. So that's why we are having here the value of t x0, t square x0, tv plus p. Okay, plus p. Okay, so the value is t of t square x0. Okay, so this is the value of, okay, so it is coming out, so the value of x cube is coming out to be t cube x0 plus t square b plus tb plus b. Okay, so what we get in the last as xk can be written as tk x0 plus tk minus 1 plus tk minus 2 and so on plus I into p. Okay, now we have assumed here rho of t is less than 1. So limit from the previous lemma k equal to infinity, tk x0 will be 0. This implies that limit x raised to power k equal to, this implies that if this is a condition, then I minus t inverse exists from the previous lemma, so exists, so I minus t inverse b from the previous case. I minus t inverse xk, this value is what? This is equivalent to 0. So what we are getting? We are getting here that I minus t inverse b will be what? It will be equivalent to 0 because from there we are getting this function. So I minus t and xk converges to x. Why? Because limit k is tending to infinity, tk x0 equal to 0. So this implies that I minus t x equal to b, so x equal to tx plus b. Okay, okay, how does it exist? Let us explain it. Because rho of t is less than 1 we have taken, then by the previous theorem we can say limit this x0 is equal to 0. This implies that limit x raised to power k is tending to infinity, limit tk x0 plus limit tj, j equal to 0 to infinity. If we are taking k is tending to infinity, that means this case, this thing. Okay. So this is what b here also, j equal to 0 to infinity. So what does it imply? It implies that this term is what? This is 0 here, this 0, limit k is tending to infinity, xk plus this sum. This sum can be written as I minus t inverse b. Okay. Xk converges to x, that's why we can write it x equal to this thing, x from here, x equal to I minus t inverse b. So this implies that I minus t x equal to b. So ultimately we are getting x minus tx plus b. So x is converges to tx plus b. Okay. So this implies that the sequence xk converges to tx plus b. Next we have to show the result that xk converges to x, then rho of t is less than 1. So let us assume xk is converges to x, then x minus xk will be what? The value of x will write as tx plus b minus the value of xk is what? t x k minus 1 plus b. Okay. So this can be written as t x minus xk minus 1. So it is t x minus xk, just check. What is the value of x minus xk is t into x minus xk minus 1. This implies that x minus xk minus 1 will be what? It will be t x minus xk minus 2. Okay. So we can write here x minus xk as t square, just put the value of x minus xk minus 1 into this. So t square x minus xk minus 2 and so on. We are getting here x minus xk equivalent to tk x minus x0. Let z equal to x minus x0, then tk, just put x minus x0 as z. So tk z will be what from here? X minus x0 will take as z, arbitrary factor. So tk z equal to limit k is tending to infinity x minus xk. Okay. So what we are getting? X minus limit xk k is tending to infinity. It is already assumed. xk converging to x converging. So what is this coming out to be? X minus x0 equal to 0. So this implies limit k is tending to infinity tk z equal to 0. This z is any arbitrary, so this implies that tk is convergent. This implies that, and when limit tk equal to 0, k is tending to infinity from previous lemma, this implies that rho of t is less than 1. Hence proved. Okay, so the proof is done. Next topic is error bound. Error bound. Let x bar is belonging to Rn. It is the approximation to the solution of the linear system defined by Ax equal to b, r equal to, let us assume r equal to b minus ax bar. Let the r is called residual vector. Means what? Since x bar is the approximation to the solution of the system Ax equal to b. Okay, so when we'll write Ax, if we are writing Ax minus b, it is coming out to be 0 when x is the exact solution. But we are replacing x by x bar, that is the approximate. So what we are getting? We are getting some error. That error we are representing by r, that is called residual vector or the left one. Okay, so we are getting, so r is what? R we can write it as b minus ax bar. We can also write this is equation number 1 and this is equation number 2. So what we are getting? R equal to b minus ax bar minus ax plus b. Yeah, just take this way. Let us write b minus ax, so that it will be okay. So this is minus, it is coming out to be r equal to a x minus x y. Okay, if r is small, then or just take the norm of this. If norm of r is small, then norm of x minus x bar should be small, obviously. Why? Because then when the approximation is near to the exact solution, then only r will be the small, should be small as well. Okay, but it is not always the case. It is not always. We can see this with the help of example. It is not always. Okay, so let us explain it with the help of an example. Ax equal to b is given to you. They are 1, 2, 1.0001, 2, and x1, x2 equal to 3, 3.0001, and the unique solution of the system is 1 transpose 1. Then find residual vector for x1 equal to 3 minus 0.0001 transpose. Okay, so this is what? This is your approximate solution, and this is the exact solution. Okay, so residual vector is what? B minus a x1. So what we are getting? B is what? 3.0001 minus 1 to 1.0001 to This is 3 minus 0.0001. It is coming out to be 0.2 and it is 0. So norm of R is coming out to 0.82. R is small, but norm of x minus x bar, if we'll find out, it is coming out to be 2. So this implies that x bar is not a good approximation to x. Approximation to x. Okay, here this is small, but norm of x minus x bar is not small. Okay, so next is, there is a small theorem. Suppose that x bar is an approximation to Ax equal to B. A is a non-singular matrix. R is the residual vector for x bar. Then for any natural norm or for any norm of x minus x bar is less than equal to norm of R into norm of A inverse. And if x is not equal to 0 and B is not equal to 0, then norm of x minus x bar upon norm of x is less than equal to norm of A inverse, norm of R upon norm of B. Or we can say that we have to find out the error for the bound for norm of x minus x bar. X minus x bar is what? That is the error between the exact solution and the approximate solution. So error is less than equal to norm of R into norm of A inverse, or this is another. So we are getting here two bounds that we have to compute. So the maximum value of the error bound will be what? That will be norm of R into norm of A inverse, or norm of A into norm of, for the relative error, we are getting this bound. So let's do the proof. You know R equal to what? B minus A x bar. Just keep in mind, here we are using this small b, so I should write here small b. Okay, so this is that b minus A x bar. B is equal to what? That is Ax, we can write, this is Ax bar. So we will replace B by Ax. A is non-singular, it is given, and A is non-singular, that means A inverse exists, so we can write R equal to A x minus x bar. This implies that A inverse exists. So we'll take norm of R, or I should write first like that, A inverse R equal to x minus x bar. Taking norm, so what we are getting, x minus x bar, by the property of the norm or by the definition of norm, we can write norm of A inverse norm of R. So this is the first case, the absolute error. Now the second case, moreover, since b equal to Ax, so we have norm of B is less than equal to norm of A into norm of X. Okay, so we can write here 1 upon norm of x less than equal to norm of A upon norm of B. From here, just we have taken norm of x in the denominator and norm of B in the denominator of the right hand side. Okay, so divide equation number 1 by equation number 2. What we are getting? Norm of x minus x square upon norm of x. So just put the value of norm of x here. So what we are getting? We are getting norm of A into norm of A inverse upon norm of B into norm of R. So this is the relative error, and such result is proved. Next is ill-conditioned system. A matrix A is said to be ill-conditioned if a small change in the coefficient matrix or vector we produce a large change in the solution. Then the system is called ill-conditioned. Okay, now ill-conditioned system is defined in terms of condition number. That K is called condition number, and the value of the condition number, and what is condition number? That is norm of A into norm of A inverse. If K of A is less than equal to 1, system is well conditioned. Is well conditioned. If K of A is greater than 1, system is ill conditioned. Okay, let's take one example. Suppose A is a matrix given to you 1, 2, 1.0001, 2, then norm of A infinity equal to maximum of summation 3 and 3.0001. Okay, what is the definition of norm of A infinity? Summation row wise, and then we'll take the maximum value. Okay, so A inverse, find out A inverse. It is what? Minus 10,000, 5,000, minus 5. Norm of A inverse 20,000, and the condition number is here, that is very large. So matrix A is ill-conditioned system. Ill-conditioned system. Okay, so this lecture will finish here only. In the next lecture we will discuss about the power method to find out the eigenvalue or largest eigenvalue and the smallest eigenvalue of the matrix A. Thank you.